All right, welcome, ladies and gentlemen, to this fantastic new innovation that we are presenting using Python RocketPy. There are features for liquid motors that are being improved at all times, especially when we start using them in conjunction with real projects over here in the UK. So we have begun this, shall we say, new approach to making live calls in conjunction with live events so that we can investigate how RocketPy can be used beyond the simple and basic exemplars that are put online. So my name is Nicola Jane Buttigieg. I have recently left the GDST, but up until Friday, I was running their space technology diploma, and RocketPy was one module that we used, keeping in mind this was for computer science students who were learning to use Python in the area of space technology. So during that 2 years where I was working with Guy here on making curriculum materials for RocketPy, we discovered that Python itself is quite a tricky thing to learn, but the way to do it is to make introductory Python exercises specifically for RocketPy or aerospace engineering. Another software I'm using is GPKit by Dr. Woody Hoberg, who was an astronaut. Similar scenario there. Now, I got in touch with Dr. Alistair John, who is also joining us on the call today, because on Thursday, he's got an event which he's going to tell you all about. Now, I'm going to share my screen, but Alistair, we'll just check that your mic is turned on, because I'm going to hand over to Dr. Alistair John to tell you all about the event on Thursday, for which this amazing tutorial is geared.
Thanks, Nicola. I'll just wait for you to share the screen. Yep. So hi, I'm Alistair, and I run Race to Space, which is a UK-based competition for test firing liquid and hybrid rocket engines. So the link here, obviously, is we've got lots of students starting to develop liquid and hybrid rocket engines in the UK and looking to launch those. Actually, our Sheffield team recently launched the highest liquid rocket in Europe by any student team. So on Thursday, we've got our main symposium, which is our big kind of networking event. The last 2 weeks in the UK, we've had all different teams hot firing their rocket engines. So you'll be able to see all of that online. The point of this talk, I guess, is if anyone's interested in getting involved in that or doing wider kind of liquid rocket engine research and kind of education collaboration in the UK or Europe or even the US, we're doing this, and it would be great to hear from you. And yeah, feel free to get in touch. Thanks.
Now, Dr. John, would you like us to play your short video promo? Because I have that here.
Okay, brilliant, thanks. Yep. So in 2024, which is obviously now, we've got 19 different UK universities all building and developing liquid or hybrid rocket engines, and they'll all be kind of celebrating that at the end of this week. But get in touch if you want any more information on that. There's a website link there. Thank you.
Very good. And as it says, there's nothing else like it in the world. Is that right, to your knowledge?
Yeah, I think so. I mean, in the US, it's a lot easier to test stuff yourselves, but there's no organized propulsion competition. There's obviously Spaceport America Cup, where you launch all sorts of things, and people can go to FAR in California. But it's quite difficult for students to get access to static hot fire testing. The German teams can do it at DLR, but in the UK, there's only really one place to do it, and we're starting to grow that. So yeah.
Fantastic, Alistair. It's brilliant. Okay, so carrying on, the point of today is to look at the tool that RocketPy uses for 3D trajectory, which is a tool that isn't used in other software packages. However, it does require Python skills. So we're here today to show you the approach to using RocketPy, and just to give you an introduction, especially for people that don't code in Python, so that you can understand, because it's coded in Python, you can do other things with it. Now, Dr. Alistair John and I met through Vanessa Voini at Airbus, because at the University of Sheffield, he had an initiative, I believe it was with Project Sunlight, where they went out into the secondary schools and they were building small model rockets for the UK ROC. Now, my students hadn't gone near rocket competitions, but they did know how to code in RocketPy. So we've come full circle from the other direction. And we came to the conclusion that what we really need to do is fuse those two things together and make people aware of what RocketPy actually is and what it can do beyond the scope of some other softwares. Now, right here in front of you, a huge project has happened this year, and I was talking to Alistair about the drag coefficient. It was something I was learning about, and predicting that is quite tricky, because as you can see there, you've got launch locations, weather conditions, topography, mass and dimensions, the type of materials you're building your rocket with, and these are all inputs into RocketPy. But also, we've got NASA data that can be used, downloaded freely. People don't even realize the tools there are to download this for free. Now, I knew that because I was running the Space Tech Diploma, but a lot of people in rocketry don't know that it's available for free. And also, NASA offer outreach to show you how to access that. Now, as a result of that, we've actually built a quantum project this year. We're starting to put together, with the Q-Tech Academy and the National Quantum Computing Center's support, this idea that we could mass machine learn all the weather conditions, every type of rocket, every type of location. Could it be possible to put that onto a quantum machine and do in a number of seconds? So that is also running parallel, but it's happening because of RocketPy, for the reason that RocketPy can actually generate synthetic data, right? So in the first instance, when you've got the sensors, if they stop communicating as the rocket's launching and it cuts out before it reaches apogee, you can actually use past rockets that have launched in similar conditions and then use their result data to machine learn and predict what the apogee would have been. Now, if you can do that, imagine all the other things you can do. So we're actually using RocketPy also as a synthetic data generator. I'd like to see another software even try and do that. And that's just a little demonstration there. You'll see at the top in red writing, thrust, inclination, rocket mass, last altitude, and apogee. Now, if you imagine those, along the top here, it says training data and query data. If those are all inputted there, it does something called matrix multiplication, and it actually gets transferred over to a software called Qiskit, which is a Python quantum simulator, and you can actually run that model on a real quantum computer. And we've been in touch with Amazon about that. So if you don't know, a quantum computer is a very big, very cold contraption under the ground that works with gates and uses lasers. And it runs things in a number of seconds that normally would take something like Amazon Cloud about 47 years to run. So very, very exciting stuff. Okay, now could I just get Guy, could you just quickly share the NASA flyer that we're going to put into the chat? Okay, now, I believe that is in the chat already. Is that right? I don't know if everyone can see that.
I can resend here.
Yeah,
Okay.
just in case they can't see it if they've joined later. Now, Gui, if you can just scroll through the slides very quickly, I won't spend too long on it. These are links and just some information. So we have a partnership with NASA Earth Science Data Systems who are involved with the Quantum Project. And I've been telling them all about my conversations with Gui and Alistair up at the University of Sheffield. And these are, I've put some links in there. These are all the tools that you can use to download all different kinds of data that could impact a rocket launch. And they do actually offer free outreach to help you learn how to use those. And it's open internationally. And I know so because I've been using it with my space tech diploma for the last few years. And I have a whole network of team members there. And just to finish off before I hand over to Gui, when I go to King's College London next year, I will be doing that PhD in aerospace upskilling, if you like, in Python using generative AI. So my relationship with NASA will continue, and with Gui it will certainly continue. I hope with Dr. Alistair John it will also continue. But we are working towards upskilling using AI and using all these possibilities for learning on the job while you're trying to build your rockets, because this is the way of the future. Okay, thank you very much. Lovely to meet you all. And I'm going to hand over now to Gui.
Yes. Hi. Hello, everyone. My name is Guilherme, and right now, together with my colleague Adriano, we're going to start the presentation on RocketPy and starting the presentation. So, Adriano, the word is yours. Please be my
All right,
guest.
all right. So nice to meet everyone. I am the general manager here at RocketPy, and before we jump to the cool stuff of hybrid motors, liquid motors, and simulations, I will present something about how does what is RocketPy actually. So uh, we'll RocketPy has born because of needs that teams and rocketeers around the world have to simulate their rockets. They need a fast, reliable rocket trajectory before they launch their rockets. So we came up with an open source simulator, RocketPy, that we intend to be the next generation of trajectory simulations, right? So some of our key features are that we have 6 degree of freedom simulation that's highly flexible and allows very broad range of possibilities and optimizations. And also we are built in a very modern platform. We are an open source GitHub project with extensive documentation, and we have many validated our software many times in competitions and articles published. The main article we have published is the one in the previous slide. That's basically our birth certificate here at RocketPy, stating that we can simulate the rockets in a rocketry level very right. Okay. Talking about some other key features, we have some Google Earth integration, and you can see your your rocket trajectory, let's say in a 3D Google Earth map. That's a very cool feature. We also can do some environmental analysis with statistical data. That's very good if you are simulating a rocket throughout various conditions and, at, for instance, deciding ideal time of the year to launch a rocket, or compare this time of the year you are intending to launch with previous years. And we also can simulate different scenarios. So the main scenarios are the nominal flight that everyone hopes to have a nominal flight, but we also can simulate a ballistic and semi-ballistic flight, and everything in the range of the normal to ballistic flights, right? Because of all this reliability and features that we have become the official simulator of the EUROC competition. So the European Rocket Challenge that happens yearly in Portugal has chosen RocketPy to be its official simulator. So every team that participates in this event has to simulate their rockets using RocketPy, and also the competition itself uses RocketPy to optimize their operation and for safety reasons like evacuating some areas for that might have some rockets falling down, right? So
Okay.
I hand over now to Guy. Let's go to the cool part of this presentation.
Yeah, thank you. Thank you so much, Adriano. I will firstly introduce a short summary, a short introduction on the liquid motors, and then you're going to have a demonstrations using Python and RocketPy to make these simulations happen, right? So the first thing you have to understand is that a liquid motor is a system composed on basically these different components. First, we have a tank that is responsible to contain the fuel, and the second is a tank that is responsible to contain the oxidizer. Both fuel and oxidizer are maintained here in liquid states, and they will be injected to a combustion chamber where they will be mixed at high pressure and temperature. This, when they are mixed together, they create the so-called propellant. And as both fuel and oxidizer are in liquid states, this is called the liquid propellant. Here you have some examples of most popular, most famous liquid propellants. So for just to mention, oxidizer hydrogen, which is usually found in cryogenics, or we also have monopropellants such as hydrogen or hydrogen peroxide, or even hypergolic propellants and mixes of nitrous oxide and ethanol. And well, just to better illustrate this, I have came up with an animation that I got from YouTube channel called Learn from the Base. I love this channel, and well, here you can see the basic principle of this kind of motor. So both fuel and oxidizer are being injected to the combustion chamber by the use of these different pumps, and once they are being fed to the combustion chamber, they start being mixed, and during this mix we start an ignition, and this ignition will be responsible to start the motor indeed. So when we start the ignition, we create a combustion, and the reaction will happen, and this combustion is the responsibility to create this thrust source, this force that will be responsible to make the rocket fly away. This is the basically behavior of a liquid motor, and this can also be found in the literature as a bi-liquid propellant motor because it uses two different liquids to make it happen. To model this on RocketPy, what you're going to do is to make a simplified representation of this motor. And in order to do so, we are going to require some different inputs. So first of all, the user must provide a thrust curve, which is usually already been taken from either an empirically test or a simulation in another software. But you also need geometric properties. So for instance, the motor dry mass, the moment of inertia of this motor, the center of mass of this motor, as well as the nozzle outlet radius and position. And of course, we need to model the tanks here. The tanks will be the most crucial part of our design. And in our case, we're going to divide in example here as an oxidizer tank and the fuel tank. There are different ways of defining these things on RocketPy. To be more specific, there are 4 different ways to define them. I will briefly explain 4 of them, but on our example, we are going to use only one of these subjects. Right. The first one is a mass flow rate based tank, which is used when you already have collected a mass flow rate evolution curve. So imagine you have performed a static hot fire test, and you probably already measure some of these measures, And if you can start a mass flow rate based tank based on this curve from the mass flow rate. The second option is when you know the evolution of the mass of liquid and gas throughout the time. The third one is when you have defined or determined the level, which means the height of the liquid in inside the tank. Imagine that the tank is vertically, and as the combustion happens, the liquid height always decrease. And the final option is the Eulish based. So Eulish is the volume of the tank that is not being occupied by the propellant, by either the fuel or the oxidizer. So imagine this empty volume, and as the combustion happens, this volume tends to increase over time. So this kind of data may be obtained either by some thermodynamic simulations that can be done in other softwares, or even through empirical hot fire tests. RocketPy supports both different options of inputting data. And what we're going to do is that based on these inputs, RocketPy will evaluate the evolution of the center of mass of the motor, which may contribute to the rocket trajectory, as well as other important properties such as the exhaust velocity or the moment of inertia, right? And this is the part of tanks, and this is the part of liquid motors. But what else do you need in order to make a RocketPy simulation? So simulating a rocket on RocketPy is as simple as this fluxogram. We just need to firstly define a motor object that will be applied to a rocket object, and we call this the physical containers, the physical attributes. They are responsible for saving and storing physical data of the rocket. We combine these along with the environment, which is responsible to contain the data from atmospheric models, and those three different components altogether represents the initialization data. With this data, we instantiate a flight class, and with this flight class, we finally simulate the trajectory and visualize the results. Okay, and right now I will start the demonstrations. We have this we have this Jupyter Notebook, which is an environment where we can run RocketPy and Python. I will be sharing my screen, but just for you to know, all these contents will be available after the presentation. Okay, so here we have the example. I'm running these on Google Collaborator, which is a free open source tool from Google that allow us to simulate, that allow us to run a Python, and on running in Python, we are going to make our RocketPy simulation. Okay, first step is to install RocketPy. It's pretty simple. You just need to use pip as the package manager. In our case, we're going to use the latest version of RocketPy, which is version 1.4.0. And well, let's go. I have already previously run these before the presentation, but I will be describing each of the cells which are done on Python code. So the first step is to define the fluids that we'll be using. In our case here, we need to define an oxidizer fluid, which will be nitrous oxide, and the fuel fluid, which will be ethanol. It's important for us to define to tell RocketPy what's the density, what's the average density of these fluids at a certain temperature, and we are going to do this for both liquid and gas states of each of these fluids. Okay, so I first define these fluids, which are instances of the fluid class that can be imported from the RocketPy point motors module. Once we define the fluids that we'll be using, we can start describing the tanks. Before the tanks, actually, we need to define the tank geometry. Even though we are going to use two different tanks, I'm going to define only one tank geometry, and I will demonstrate to you that we can share this tank geometry to to more than one tanks. So we are going to define a cylindrical tank. Here we have to supply the radius and the height of this tank. And in your case, I'm setting this variable, this argument spherical caps to true, which means that the pressure vessel will be rounded. I will have spherical rounded spheres on the tips of my tanks. After defining, we can use some methods to already see some statistics about this tank geometry, most importantly, the total volume of each of these tanks. After that, we can finally start defining our tanks. Let's start with the oxidizer tank. In our case, we are going to use a mass flow rate based tank. And for doing so, we need to tell RocketPy what's the behavior of the mass flow rates during the time. In our case, I'm using an example here. This is a exponential function that may be representing the mass flow rate through the time. I can even define a function just as a Python function, and RocketPy will already use this to generate the oxidizer tank. I have printed out here two examples. It's the evaluation of this function at the point t equals 0 and the point t equals 5 seconds. And we are going to take this function and use to initialize our oxidizer tank. Okay, to initialize the oxidizer tank, it's pretty simple. We just need to import the mass flow rate tank a class from the rocket motor, the same rocket motor module, and then we need to supply with the mandatory and important input arguments. So I can define a name for these. I can use the geometry that I have already set. I need to say what's the total flux time, what's the burn time of this tank. Initial liquid mass, which in this case would be 32 kilograms, just as a matter of example here. And here is the magic. I will be using the mass flow rate function that I previously defined in the cell below, in the previous cell. Okay. After we define this oxidizer tank, we can already anticipate how is that going to be on RocketPy. So just as a matter of comment here, in case you need to understand the meaning of any of these variables, you can by any time run something like Python help and the name of the class, so you can access the entire documentation of that class, which allows you to understand the meaning of each of these arguments and also understand what is all the available methods, available functions within that class. Okay, so here you can see the tank geometry in a coordinates. It's a 1.2 meters length that tank. As I said, they are rounded with spherical at the caps. And we can already anticipate how the center of mass of this fluid will be behaving during the simulation. So it starts at some point near minus 0.15, so something like here. And as the time goes, it starts decreasing up until minus 0.55. So imagine you have this tank and you round this, you rotate this clockwise, and you're going to imagine that the liquid starts at the full tank. So the center of mass is near the center, and as it starts decreasing their volume, the combustion starts happening. The center of mass will always decreasing up until the end, where we're going to see the tank totally empty. All right, for the fuel tank, we are doing pretty much the same thing with just one adjust here that I want to show to you that we can pass a function for the liquid mass flow rate and another function for the gas mass flow rate. Once again, these are just an example, so I'm defining these as a function, but you can imagine that for the case where you already have a empirical data, you could easily load a CSV table describing the time and the mass flow rate at that specific time, and RocketPy would be able to use that as input. we run a similar procedure. So we have here the geometry of this fuel tank, and we can already anticipate the center of mass of this fluid. Later on, we can finally define the motor, which will be composed of the two tanks that we have already performed before, and also some other different data. One important aspect of the definition of the motor is to define the thrust curve. Once again, I use a Python function to do this. So here I have, as a function of time, this expression that describes or illustrates the thrust curve. But once again, you could easily import this from a CSV file, for example, in the case where you already have computed this or you have already collected this thrust curve from your empirical experiments. So we can now finally import the liquid motor from the very same module we have been importing RocketPy classes, and we are going to supply as a thrust source the thrust curve function. We define a dry mass for the motor. We define the moment of inertia, which may impact in the trajectory, and all those other different arguments that I showed to you before. Most important, it's time now to add, to actually associate the tanks to the motor. So we'll be using the method add tank, which is pretty simple. We just need to say which tank we are adding at that time and at which position we'll be adding. And after adding these two tanks, we can use the info method from the liquid motor class to visualize some results. So here we have already computed the thrust curve from ranging from time 0 to 5 seconds. It already calculates the total propellant mass, the total impulse, which may represent the area underneath this plot line. And we can also already visualize a drawing of this motor, which is the same representation we were doing before. So once again, we are dealing with a system here that is basically summarized on oxidizer and fuel tank, and also there's the representation of the nozzle. Here we can see what RocketPy calculated as the motor center of mass. So once again, if you take a look at this coordinate system where 0 is here and 3 meters on the right, we can see that the center of mass starts at some point around 1.45. So it should be here at the beginning of the flight. And the center of mass starts decreasing up until a minimum point, and it starts increasing again. So the center of mass does something like it moves to the left and then moves back to the right at the end. This is a behavior really hard to predict when you are defining the tanks, but RocketPy is already able to compute this and give you the center of mass evolution. This is of key importance for flight simulation because the center of mass of this liquid, the center of mass of this motor may impact the trajectory simulation behavior. Okay, after defining the motor, we can finally simulate the flight. So I'll be defining an environment. This is just a simple environment. I have picked randomly some latitude and longitude. I will be defining a constant wind, even though you can connect RocketPy to retrieve the latest weather forecast at your location. And we have some plots here as well where you can see the wind speed and how the RocketPy have calculated the speed of sound and density profiles at that location we are going to launch. Later, we define a rocket object, which defines everything beyond the motor that is contained in the rocket that we'll be flying. So, for example, we define here, we add a nose cone to this rocket. We add trapezoidal fins for stabilization. We also add a parachute for this object. After defining this rocket, we can see some of their details, and again, we can draw their representation. Some key important aspects of a rocket are the stability or center of pressure, center of mass, and RocketPy already gives us really easily, right? Finally, we can instantiate a flight class. We basically tell where we are heading the rocket at the beginning and what's the inclination or elevation of this launch. And running this simulation is pretty simple. It takes up to 1 second, sometimes even less. And after running the simulation, we can finally see the results. So here you have some information for the burnout state. So the burnout, the motor stopped burning at this altitude, so almost roughly 1 kilometer above ground level. We also have the apogee state, which in this case will be showing this rocket flight climbed until 7 kilometer, and many other details that you can access of your flight. Of course, we can plot this as RocketPy is a 6 degree of freedom simulator. We can plot this 3D trajectory of the flight. But what I like the most is to export this to a KML file, which is the standard file for Google Earth. So I have run this before, as I said, and this file have been created. As I'm using Google Colab, I can go here and download this file. Once this is downloaded, I can open this automatically on Google Earth. And so let's see where RocketPy is sending us on the Earth. It's right in the middle of England. As I said, it's a random location. I don't know if any of you know this place, but this is a 3D trajectory. So the rocket starts flying from this point, and you can analyze the trajectory directly on Google Earth. And well, this is pretty much the basic we can do with RocketPy. You can go even beyond that. You can perform even more accurate simulations with that. We are using an example motor, so it doesn't really exist. But if you want to see a real liquid propellant motor being simulated with RocketPy, I recommend you to take a look at our documentation. Oops, let me put here. At our documentations, we have an example from the Space Enterprise at Berkeley. It's a rocket design team from the University of California at Berkeley. They were pretty much the first the first team to use RocketPy simulations to simulate their liquid motors. I also have added some other resources here in case you want to go further, but the main resource you could find is searching for docs.rocketpy.org, and you're going to see our documentation. We have an effort, a daily effort of keeping this documentation updated. You can easily go into the beginner's guide, or if you are already experienced with Python and in programming, you can go directly to other different pages. All right, so this was our basically demo. I would like to now to invite you all to follow RocketPy on the medias. It's important for us that you also contribute and send us suggestions and feedbacks. And with that in mind, we have prepared this really short questionnaire, really short answer, really short a Google form that you can send some opinions and some suggestions based on not only on this presentation, but also on whatever you already knew about RocketPy before this event, right? So I would like to invite you all to participate on this Google form now. And in the meantime, I think we are good to open for questions. We can receive questions from the audience and start addressing them.
I think an important thing to mention on that survey there, the questionnaire there, what we're really interested in knowing is what people are expecting from RocketPy. If they invest the time in learning how to use it, what are your expectations? That's a big one. And what I'm quite eager to enforce here is that knowing how to code in Python shouldn't be a barrier to this, I am quite eager to offer some introductory Python for RocketPy type sessions. I do believe once you know what you're doing, if you're not a coder, I don't think you'll find it all that tricky. It's just getting past that first hurdle. It's a bit like learning the piano, isn't it? You see all the dots and lines. When you start to understand how they work, then you start enjoying it more. But if that is something that you could contribute there, I know Gui and I are working also on a publication. We're just curious to see, what people would find useful in a software. Is that right, Gui?
Sure, absolutely. We are always basing our development. I mean, RocketPy is still under development, which means that although you do have some very nice features already done, we keep improving, we keep developing on top of this. And all these development are mainly based on user feedbacks and user suggestions. And so your contribution here is of utmost importance for us.
Another thing I would like to take a moment to just announce while everyone is on the call, I am very eager to start collecting some real sensor data from real rockets, because in order to improve a software and the possibilities for its use, aside from just simulations, for example, for the quantum project, the more real data we have, the better we can work towards the synthetic data being realistic. So I don't know if there is any possibility or ideas. I will be at King's College next year. If there's any ideas for a collaboration whereby we make a repository, for example, where we can put real data in and the conditions under which the data was collected. I'll just throw that out there if people are listening. How do we want to do the Q&A? Shall we have them in the chat, or Gui, do you want to man that?
Yeah, sure. We already have one question on the chat. If somebody wants to open their microphone and raise the question, it's totally okay and good as well. I will answer this first question from Emery, which is, from which database does RocketPy get fluid data of nitrous oxide and ethanol, defining the example? Is it possible to extract fluid properties directly from refprop for more complex mixture? So yes, this was a simple example. So just to illustrate how to use it. So, but the answer to your question is a total yes. You can use more complex data. You can integrate this code with other with specialized thermodynamics simulators. I would say you mentioned here refprop, or there's also coolprop. And those are very good sources of thermodynamics properties for this kind of fluids that will be used in the simulation. The thing using RocketPy is that we do not make any thermodynamic calculation behind it. We just rely on the input data that the user is supplying to us, which actually gives us flexibility for you to for you to set up your simulation with the most accurate data that you have, and then you just input on RocketPy. In RocketPy, we make the flight trajectory simulations, the 6 degree of freedom simulation, which is what RocketPy can do that other softwares can't. So answering your question, yes, it is possible to do more complex mixtures. I should ask you again to take a look at the example on our documentation. I think I can even show here at the flight examples page. We have the Space Enterprise at Berkeley example. You are going to see that we have here data come from a real rocket. So it's an empirical data. It's not just, for example, the mass flow rate here. It's not just the simple example that we have shared during the call. Okay, so if that addresses the question, I think I'll follow through the next one, which is from Oliver. I was wondering, can I use these for hybrids as well? Yes, thank you very much for a question. I have forgotten to mention this. But absolutely, RocketPy does support liquid, solid, liquid, and hybrid motors. I have here some hybrid motors usage examples. The hybrid motor, though, is as simple as uh, a mix of the solid motor with the liquid motor. So basically, you're going to define the solid propellant, but also create a tank for the oxidizer, and then you create the hybrid, just in a very similar procedure. Okay. And I think that there's another question: does RocketPy currently have support for fuel additives? Okay, this is a very good question from Ibrahim. It does not directly. You cannot just add a fuel additive, but depending on the simulation you are trying to do, you could do the simulation without needing to define the additive. You could create either another tank or just create a mix of fluids instead of with a average density of them, instead of just one just the few fluids. There's somebody that has raised their hand, and I would invite you to make your question.
So thank Jen. He's got it in the chat there. I'm trying to simulate
Okay, it's kind of in the chat.
a launch. Oh, you read it. I'm trying to simulate a launch from the irregular data, but can't find the GFS and forecast data.
Yes, okay. Forecasting data is a feature of RocketPy. Here you can go onto the environment class usage and search for forecast. We do support several different forecast models. The most famous one is GFS. The thing is, this GFS model usually makes their meteorological forecast for up to 10 days range. So when somebody says that he's trying to run GFS, but it's not finding any data, it's not finding any forecast, that's probably because the data that you are trying to simulate is no longer available on the GFS servers. I recommend you to access our Discord server, where you could ask your question again and receive more assistance. But imagine that the forecasts are used when you are launching the rocket in RocketPy from today up to 10 days in the future. But if you're running this for a past date, you probably should be using reanalysis instead. I also see the question about RocketPy, and this is a very good question, because you can now take your Open Rocket simulation. So just to explain, Open Rocket is a very Open Rocket, a quite traditional and popular simulator software that has been using from years and decades already. And what we did on RocketPy is to create a serializer. So what you are able to do is to take your OpenRocket simulation and translate this to a Python code. You can easily search this in as on our GitHub page. So if you go to RocketPy's GitHub, which can also be accessed through rocketpy.org, pretty simple to find the address. You're going to find out our repositories, and by navigating here, you're going to see that we have a Rocket Serializer repository, which is a tool to convert your OpenRocket files into RocketPy simulations. So yes, there is some integrations on that level. Of course, we would like to improve these even more, and for doing so, having different feedbacks are quite important to us. Okay, so Adriano, Lucas, do you see any other question?
Yes. Let me just get here. So Aaron Verdon has asked, I was wondering if it's possible to add a custom draw main parachute in terms of dimension and geometry.
Yes, it is totally possible. On our documentation, if you go to the rocket section, there's the adding parachutes description, and the parachutes will basically get the CDS, which is the drag coefficients of the parachute times the area of this parachute. So it doesn't really matter the geometry of the parachute itself, just the drag coefficient times the the surface area of this parachute. So yes, you should be able to add any kind of parachutes on RocketPy.
Okay.
There's also one from Alex. He asked, is multiple stage rocket something that could be added?
Sure, it definitely can. It is totally possible to do this with RocketPy. It's pretty similar to the deployable payloads, which in essence is that you're going to define more than one flight. So here, imagine we are seeing an example of a flight that it starts the rocket is a launch vehicle bringing up with the payload, and at the apogee, the payload is ejected. So we start two different other flights. And in order to do a multi-stage rocket, you would have to do something quite similar. But yes, it is possible.
Okay. So Oliver, that you already answered one of his questions, also asked, will there be some sort of collaboration with something like OpenRocket, with already has a developed key? So I guess you answered that, but in the rocket serializer answer, but we are also developing a GUI of our own, so that will be probably come up in the next few months, so to be easier to simulate the rockets. And there is another question here from Jonas. Is it now possible to run Monte Carlo scatter simulations for liquid rocket motors parameter variability?
Very, very good question. Yes, it is possible. We do have a Monte Carlo class on RocketPy that is mostly used to create a confidence intervals of our simulation. So imagine that we add uncertainties to all the inputs data that we have. So you're gonna have to create stochastic objects. So I'm showcasing here some examples of stochastic solid motor, stochastic rocket, stochastic flight, stochastic nose cone. And for liquid, right now, I'm not sure if you do have a stochastic liquid, but we certainly do a stochastic generic motor. So we could be adding uncertainties to this motor and should work pretty much similar to the liquid motors itself, right? By the end, the idea is that you calculate, you evaluate the trajectory 100, 1,000, 10,000 times. In this case, in this example, you're running 1,000 simulations with RocketPy. As I said earlier, RocketPy runs the simulation really fast. It's up until 1 second. So you can easily create a loop and start iterating this on the Monte Carlo process. So you can add uncertainties to the output variable. So for example, here you have the apogee mean, but you also have a standard deviation, which means that you are adding uncertainty, you are adding confidence interval for your result. And yes, it is possible to integrate this with the liquid motors as well.
Is there any documentation about the derivation of the equations?
Sure, good question as well. That would be on the technical section of our documentations. We have here the equations of motion being defined for the RocketPy V1. So we separate RocketPy on V0 and V1. The V1 was a more abstract, and it's the current version that we are using, and you can follow through all of these through all of these equations. However, you can also find RocketPy article. It's pretty simple. You can, I think if you just go with RocketPy, it should be one of the first links here at the ASCII library. The paper title RocketPy 6 Degree of Freedom Rocket Trajectory Simulator, you can find on this link. There you can find the full description of the equations of motion derivation. In case you do not have access, you can contact the author directly, and we may help you with that.
Okay, so there is a question from Gabriel Paganini. For the liquid tanks, is sloshing effect being accounted?
Very good, quite good question, Gabriel. Not yet. This is a non-limitation. We'd love to add sloshing effects to this flight and see how these behaviors. And well, it's probably stay tuned, because probably it could be coming soon in a future version of RocketPy.
So there is a last question that has been asked a lot of times, that if this presentation will be available afterwards. So yes, we are recording this presentation and it will be available on the RocketPy YouTube channel, right? Oh, there is another question from Oliver here on the chat.
Yeah, for transonic and supersonic, the same answer for more complex liquid motors values for here. RocketPy doesn't really calculate drag coefficients. It rather imports drag coefficients from other sources. So you should be able to integrate Res-Aero 2 or even Missile DATSCON or other drag and lift coefficient estimators. You can easily integrate them with RocketPy, and the accuracy is usually good. I recommend I refer again to the flight examples page on our documentation. Usually we describe the comparison between the real flights, the actual measured flights, and the simulated flights, and RocketPy usually predicts the apogee within an error of 2 or 10%, 2, 5, 10%, depends on the way you model. Okay, so I think that was all.
I have a question. This could be a crazy question, and I might show my ignorance, but could RocketPy be used to launch a rocket that releases a UAV? You know, like using to get a UAV off the ground at a height. Could that work? Or has that been done before?
Yes, it can be done. It cannot simulate the drone, the UAV trajectory, but it can simulate the release of it.
Well, it's weight, right? Also carrying the UAV up, right? So it's going to be heavy too.
Yes, sure. Because you first start a flight with the rocket with all the payload, all the mass, all the moment of inertia, and at a certain point you trigger the ejection of this mass. So we have to create another rocket. You start another flight with this rocket, already accounting for the decrease of mass and the variation of moment of inertia.
So maybe an integrated RocketPy GP kit proposal in the making? Something to think about?
That's something to think about, absolutely.
How about that? All right. Just an idea, just thinking after listening to all this. You know what my brain's like, it ticks.
Yeah.
It's reached 3 o'clock. So unless there's any more questions, I guess the final thing is how we stay in touch with everybody. Do you have a way of joining the RocketPy mailing list? Thank you for
I think the best way to follow us is either from LinkedIn or Discord server would be better. Are you asking regarding?
Well, I've got a whole bunch of students from the GDST, and I've now left the GDST, so we can keep in touch through RocketPy, for example, as well, because we're working on these Python projects. Perhaps we
Sure.
can.
We also have.
We could reply back to the mail out, couldn't we, with a way of them to join?
Yeah, absolutely. We do have the list of all of them, and we can send this material. We can send the link to our
The recording as well.
the recording on the YouTube channel.
Okay, perfect.
Also, at any time, you can contact us at this Gmail address, the rocketpy@gmail.com.
That's what we want. Yeah.
And that's it. It doesn't matter the platform. We will always be there to help assist and listen to your suggestions and ideas.
Fantastic. So what we'll do, we'll do a mail out just after the call with a link to the video, the resources, and that email again, just so we can keep in touch with everyone on a mailing list. That sounds great. Thank you so much to the RocketPy team, to Adriano and Guy and Samuel. And Dr. Alistair John, thank you for joining us and for your contribution. And for everyone else for joining. And we hope to see you in future RocketPy sessions.
See you. Thank you. Thank you all.
Thanks, everybody.